13.4 we're moving on to, which is Green's theorem. Okay. And Green's theorem is a theorem that arises from line integrals. So it's the next step, logical step after making after doing line integrals. So we're going to start out here. It's getting a little bit wordy before we see an example. Okay, so sit tight. Let C, so same C that we've been talking about where it's a curve, okay, be a positively oriented, which in math, that means counterclockwise, just like your unit circle is positively oriented. We move around it in I hope I just said counterclockwise. We move around it in a counterclockwise motion. Okay, so positively oriented in math means counterclockwise. Another good way to think about it is if you're walking around the perimeter, the interior should always be to your left. Okay, so positively oriented, piecewise smooth. Okay, so it's a smooth curve. Oops, piecewise smooth. Ooh, I'm having difficulty writing. Piecewise smooth, simple, which means there's no holes in it. Okay, closed curve. In the plane. And here I'm going to draw an example of what C might be. Okay, smooth, closed, simple, there's no holes in the middle of it, and positively oriented. So we can draw the orientation in there going, if I were to walk around the perimeter of this region, the stuff, the inside would always be to the left of me. Okay, and let D be the region bounded by C. Okay, so D is this region. Okay, if P and Q have continuous partial derivatives on an open region that contains D, so at least in D, then we get this neat little theorem. Okay, your line integral over, I'm going to show it with the closed curve, your line integral over C of P dx plus Q dy, and remember P and Q would then be functions of x and y. Can you write that? P is a function of x and y, Q is a function of x and y, equals this double integral over D of the partial dq dx minus dp dy. Notice the change in order there. Okay, P with respect to y, Q with respect to x, dA. Okay, and remember we can also write this as F is like a vector field, P in the I direction, Q in the J direction, or PQ. Okay, and R, I should say dr. There you go. Okay, so dx dy. Okay, where R would be xi plus yj. That's how I want to write it. I'm not sure that I want to include that last piece there, but anyways, we'll do that. Okay. This is a theorem that's not easy to prove. It is in your book, if you would like to take a gander. Okay. And you might say like, okay, I'm going from doing a single interval to doing a double integral. That seems like the opposite direction that I want to go. But actually, sometimes it's required. Remember, if you want to do this first integral, right? One of the very first thing we did is parameterize it, okay? And that's not always possible. So sometimes if we take those partial derivatives and do the double integral instead, we're going to have an easier time, okay? And it's really interesting here, right, that this line integral along C, okay, that line integral of this vector field along C is the same as if we did this area integral over D, okay? And we can kind of get into a little bit about how, I don't know that I want to get too far with this. I'm going to leave it at that for now. I'm not going to get into too much of the deeper stuff going on here. But it comes out to the fact that like so much in the interior kind of cancels out when you're doing the area, and we're only really left with what's along the exterior because of some of the properties of that region. But I'm just going to leave it like that. Okay. So we're going to do, first of all, an example, and we're going to do it both ways. We're going to do it the way that you learned it in 13.2. I'm sorry, 13.3. And then we're also, or actually 13.2 is when you did line integrals, when you first started them. And then we're also going to do it with Green's theorem. Okay. And the one I'm going to show you is probably a little bit easier with Green's theorem, but not a huge step. And then I'll show you another one that's a little bit more complicated. Okay. So we're going to do this example. And it's actually an example in your book. I don't know that they do it both ways in your book, but we're going to find the interval over the closed region, or closed curve, of xy dx plus x squared y cubed dy, where C is the triangle with vertices 0, 0, 1, 0, 1, 2. Okay, so I'm actually going to draw that over here. 0, 0, 1, 0, and 1, 2. Okay. All right. So the way that we would have done it in 13.2 is we'd have to do 3 different line integrals. Okay. We'd have to call one of them C1, C2, C3. Okay. C1 goes from, it's a segment. So this is nice that they're segments. Okay, so we can parameterize it pretty easily. We're going to go from 0, 0 to 1, 0. So parameterized, that would be 0 plus 1t, and then just 0. Okay, where then t again is between 0 and 1 when you parameterize. We're just parameterizing the segment here. Okay, and then we'll also, so I'm going to write a little bit more over here. X is t, y is 0, then dx is dt, and dy is 0. Technically 0 dt, I guess, but I'm just going to leave it at 0. Okay. And then C2, we're going to go from 1, 0 to 1, 2. So that would be t plus 1t. Sorry, 1 to 1 is just going to be t. Oh, no, I'm sorry. It's just going to be 1. X is 1, and y is 0 plus 2t. Okay, again, t from 0 to 1. And x is 1, y is 2t. So dx is 0, dy is 2 dt. Okay, and then our last one, C3, we're going to go from 1, 2 to 0, 0. So starting at 1 going to 0, 1 minus t, and starting at 2 going to 0, that's going to be 2 minus 2t. T is 0 to 1. X is 1 minus t, y is 2 minus 2t, So dx is negative dt, and dy is negative 2 dt. Okay, so now we can do your integral along C1. Okay, so from t equals 0 to 1 of x, y, dx. So that's going to be just xy, right, would be 0. Okay, and then dx is dt. Plus x squared y cubed, which would also be 0. And then dy is actually 0 dt. Okay, so that's just going to give you 0. All right. C1 is going to lead us to 0. Then we can go along C2. Okay, so again, from t equals 0 to 1. And we need xy dx. So xy will be 2t, but dx is 0. And then x squared y cubed would be 8t cubed. And then dy is 2 dt. Okay. And then along C3, again from 0 to 1. And we have xy. So I'm going to write y is 2 times 1 minus t, because that 1 minus t is going to show up a lot. Okay. So xy is going to be 2, 1 minus t squared. Okay. And then dx is negative dt. And then x squared y cubed, so it's going to be 8, 1 minus t to the 5th. And then dy will be negative 2 dt. Okay, I think I got it all now. All right, so when I do C1, I'm going to do the integral from 0 to 1. That goes away. I'm going to have 16 t cubed dt. So that's going to be 16 t to the 4th over 4 from t equals 0 to 1. Okay, so that's just going to be 4. And then when I do C3 here, I've got, let's see here, I got a little bit more going on here. So I'm going to do the integral from 0 to 1 of, I'm going to take that negative 2 out of everything. 1 minus t squared dt plus 8, 1 minus t to the 5th dt. Okay, so when I integrate, I'm going to go it as a u sub. Just make sure that that u then dt would be negative du. Okay, so I'm going to have negative 2 times, I hope I'm getting all my negatives straight here. I think I am. Negative 1 minus t cubed over 3. Yes. Plus negative 8, 1 minus t to the 6th over 6. Okay, and we're going to evaluate that from t equals 0 to t equals 1. Okay, so when t is 1, I got nothing. Okay, and then when t is 0, I'm going to have negative 1/3 minus 8/6. Just making sure I'm keeping all these negatives straight, which I think I am. Okay, so now I've got negative 2 times 1/3 plus 4/3, which is negative 2 times 5/3, which is negative 10/3. Okay, so I have 0 plus 4 minus 10/3. 4 would be 12/3, so I get 2/3 as an answer. Okay, nothing about that was too difficult. Maybe a little tedious, but not too difficult, right? Okay, So now we're just going to do it with Green's theorem. Okay, so should I use green for Green's theorem? I think that makes the most sense, right? Okay, so again, I'm just going to rewrite the problem. Okay, so this is your P dx plus Q dy. Okay, and again, the region that I had was from 0, 0 to 1, 0 to 1, 2. Okay, so then rather going along C, I want the double integral of that area. Okay, so just that, I mean, we're going to have x goes from 0 to 1, and then y goes from 0 to the line. So this line is y equals 2x. So 0 to 2x. Okay. So I have to do my dy on the inside, right? 0 to 2x dy. And I need my 0 to 1 dx. Okay, so there's my double integral. That's your double integral over dA part of it. Okay, I still need the partials, right? The dq dx minus dp dy. Okay, so dq dx is going to be y cubed. I don't know. Oh, I wrote that. I was going to say I wrote that wrong. Okay, dq dx is going to be 2x y cubed. Okay, and then dp dy is just going to be x. So I'm going to do the integral of dq dx minus dp dy. First with respect to y, then with respect to x. Okay, so this will be the same. Okay, this line integral over c, where this exterior is c, okay, is the same as the integral of dq dx minus dp dy over that interior area d. Okay, so now I'm just left to do that integration. So first with respect to y, okay, so I have 2xy to the 4th over 4 minus xy from y equals 0 to y equals 2x. Okay, so I'm going to just simplify that 2/4 to be 1/2. Okay, so y to the 4th, so 2x to the 4th will be 16x to the 4th. So I have 16x to the 5th over 2. So I'm going to have 8x to the 5th minus x times 2x, so 2x squared. And then if y is 0, I've got nothing left, so just dx. Okay, and now integrate this, 8x to the 6th over 6, so 4x to the 6th over 3, minus 2x to the 3rd over 3, evaluated from x equals 0, which would just give me zeros, to x equals 1, which is nice and easy, so I have 4/3 minus 2/3, which is 2/3. And there you go. Much easier, right? I guess not much easier, but less work. Okay, let's do another one here. I want to get one. I had another one written down here. Maybe I didn't write it down. Oh, I know where I did it. Okay, I have it in a different set of notes. Okay, we're going to look at another example. Okay, where we want integral over c of 3y minus e to the sine x dx plus 7x plus square root y to the fourth plus 1 dy, where c is the circle, x squared plus y squared equals 9. Okay, so we could try to do this like in 13.2. Okay, where x is going to be 3 cosine t or theta or whatever you want to do. Y would be 3 sine t. We're parameterizing the curve, right? And t is between 0 and 2 pi. Okay, and then remember we have to do f dot dr. Okay, so f would be 3y, so 9 sine t minus e to the sine of 3 cosine t. It's looking messy, guys, right? And then, oops, I should do this. And then for the y part, it'd be 7 times x, so 21 cosine t, plus the square root of y to the fourth, which would be 81 sine to the fourth, t plus 1. Okay, and then since r is 3 cosine t, 3 sine t, r prime would equal negative 3 sine t, 3 cosine t, dt, right? So we would have this integral from t is 0 to 2 pi of f dot dr, which is, this is dr. So we would have, oh my goodness, it's going to get messy. We're going to have 9 sine t minus e to the sine of 3 cosine t times negative 3 sine t plus 21 cosine t plus the square root of 81 sine to the fourth t plus 1 times 3 cosine t and all of that dt. Anyone feel like doing that? Go ahead. Go ahead and try this and see if you get the same answer that we're about to get here. Okay. So the easier way to do this, okay, is, and I'm just gonna copy this guy down to here. I hope it copied. There it is. Okay, so what we're going to do instead is, oops, I didn't want to do that. Done highlighting. Green for Green's theorem. Okay, this is P. This is Q. Okay, dp dy is 3. dq dx is 7. And then we are going to convert to polar for this guy, okay? Excuse me. So when we do our limits, like, so dq dx minus dp dy is 4, okay? So we want to do the double integral of 4 dA, okay? And then since our region is a circle, we're going to now switch to polar. Okay, so we didn't have to think that far ahead yet, but now for your polar, because there's no x's and y's in that dq dx or dp dy, so it doesn't really matter. But x then would be our cosine theta, y would be our sine theta if there were, okay? And then r is going from 0 to 3, theta is going from 0 to 2 pi. So we can integrate 0 to 3, 0 to 2 pi of 4 dr d theta. Don't forget the extra r for when we switch to polar. Okay, so then we have 4r squared over 2, so 2r squared, evaluated from r equals 0 to r equals 2 pi. Oops, I mixed up my r's and my thetas. Let me fix that. Okay, so r goes from 0 to 3. Theta goes from 0 to 2 pi. Okay, and so then we'll have 2r cubed, which is just going to be 18. Integrate that from 0 to 2 pi d theta. And you know that's just going to be 18 times 2 pi, which is 36 pi. Okay, I think I did that right. I know I went through it kind of quickly. But there you go. Okay, so if you would like, see if you can figure out how to do that and get the same answer. But I think Green's theorem helped you out quite a bit there with that one. Okay, that's the basics. Okay, I'm going to show you some of the little bit grittier stuff now, I guess you could say. That's not as important, but it's interesting. One of the pieces you'll see if you ever take like some more advanced math classes than what you're in right now. But okay, the first thing that we're going to look at is the fact that the converse is also true and can be used in certain situations. Okay, so sometimes rather than doing a double integral, we would rather do the line integral. Okay, and what if, remember here, if dq dx minus dp dy is 1, then you're finding the area of D. Okay, so if that's something that you want to do, you can kind of pick. Like if I want to, if I'm finding an area, I know that this is the integral that I'm doing. If I can pick a p and a q such that dq dx minus dp dy equals 1, it's equivalent. Okay, so one way I could do this is if I have, for example, p equals 0 and q equals x. Okay, then dq dx minus dp dy would be 1 minus 0, which is 1. Okay, and then I can do my line integral of 0 dx plus x dy. Okay, and I would get the same thing. Another way that I could do this is I could do the opposite. I could do p is negative y and q is 0. Then dq dx minus dp dy is 0 minus negative 1, which is 1. And then I do the line integral of negative y dx. Okay. And that would give me the area also. Okay. And then I'd have to make sure that still, you know, if that region D, you know, I need to make sure that I can figure out C around it in terms of X, right? Okay. Or in terms of Y or whatever I'm choosing. So you still need to be able to, you know, this is if it's easier to work with C than it is to work with D. Okay. And one last option that you might see, I think this is the one that they use in the book, P is negative 1/2 Y and Q is 1/2 X. Okay. Then dq dx minus dp dy is 1/2 minus negative 1/2, which is 1. And so then I would do my integral of 1/2 x dy, oh, I kind of switched them there, minus 1/2 y dx. Okay, and in some cases, maybe that's easier. All right, I'm going to show you an example that uses all of them, actually. The book does it one way, okay? Bear with me here, because it is kind of weird. It's like, why would we do this? Well, because it's just to show that Green's theorem works that way, okay? But in the book, they have find the area enclosed by the ellipse, x squared over a squared plus y squared over b equals 1, okay? And so this one too, like it's a little bit hard to work with that area D. You know, we could get your parametric equations of an ellipse, okay? X equals a cosine t, right? Because the a goes with the x part. Same as a circle. It's just instead of with a circle, it'd be a squared and b squared, right? Those would be the same numbers, okay? Y is b sine t. All right. So then dx dt would be negative a sine t, and dy dt would be b cosine t. Okay, so again, if we could do the double integral of 1 dA over d, where d is this region, okay, but what the tricky part is here is that we're probably going to want to use polar for this, and definitely theta is between 0 and 2 pi, but what's r between? Okay, it varies, right? On the x-axis, it goes out to a. On the y-axis, it goes out to b. It hits everywhere in the middle. That's the tougher part. So trying to come up with that is where we'd kind of run into some problems. Or if you didn't parameterize it, we'd have to get your functions, in terms of x and y, which we kind of don't want to do. It's much easier to parameterize the border of that region, which we just did here, than it is to try to parameterize the inside of that region, okay? All right, so let's keep going here. Let me figure out in my notes here. Okay, so again, I guess I should have written t here. Okay, so again, trying to do that area integral is tricky. What's not going to be as tricky is if we try to integrate over the closed curve with respect to t, because we do know that dt is, or t is between 0 and 2 pi. Okay, so this is a good example of when that line integral is easier than the area integral. Okay, so again, we can use any of those relationships that I drew up here in red to do this. Okay, they're not specific to any problem. They're just, these are some combinations of P and Q that would work, and you could come up with infinite ideas here, but these are probably going to be the 3 easiest ones. Okay, so if we do, let's switch colors again here, I'm getting sick of purple. All right, if we do P is 0 and Q is X, okay, then dP, let me get it right here, I don't want to mess up this, dP dy would be 0. Ooh, hold on. And dq dx would be 1. Okay, so we would do the integral from 0 to 2 pi of, and again, I'm just going to rewrite Green's theorem here so I don't have to keep scrolling up to show you. Remember the integral over c of p dx plus q dy is the same as that dp dx, or sorry, dq dx minus dp dy dA. Okay, so remember, this is what we showed, that these choices for P and Q are going to work, okay, because then that would give us the one there that we would want when we're finding, we want that to be 1 to find the area. Okay, so P is going to be 0, dx is negative a sine t. Okay, so that's just going to be 0. And then Q is x, and dy is b cosine t. Okay, well, if Q is x, that's a cosine t. Okay, and then, excuse me, dy is b cosine t. And then we got our dt. Okay, so again, I'm going to kind of back up a little bit here, maybe switch a different color here. We don't want to do this because it's too hard to do that area integral over an ellipse. Okay, so we're going to do this instead because it's easier for us to parameterize the border of the ellipse than the interior. If we are going to parameterize the border, this is how we do it. Okay, we have strategically chosen P and Q so that dq dx minus dp dy would be 1. Okay, so now we're just doing the subbing in here. Okay, so again, P is 0, so we don't have that first part there. Q is x, which is a cosine t. And then dy would be b cosine t dt. Okay, A and B are, excuse me, A and B are constants. So AB integral 0 to 2 pi of cosine squared t. And then we know that we have to use a trig identity for that. Integral from 0 to 2 pi of 1 plus cosine 2t over 2 dt. I'm going to take the 2 out, so we have AB over 2. And then the integral of 1 would be t. And the integral of cosine of 2t would be 1/2 sine t. 2t, I'm sorry. Okay, and then we will evaluate that from t equals 0 to t equals 2 pi. Okay, and you can see that second term will just always be 0, the sine of 0, the sine of 4 pi. Okay, so the first term is going to be 2 pi minus 0. So we have AB over 2 times 2 pi, which is pi AB. Okay, and that is the area of the interior of an ellipse, if you didn't know that, right? If it's a circle, A and B are the same thing. So you'd have pi A squared or whatever, and A is the radius, okay? If we were to choose the next one, I'm going to leave it up to you. I think in the book they do P equals 1/2 y and Q equals 1/2 x, or one of those is negative, the first one is. So you could go through and do the same thing. And then the other option was that P equaled negative y and Q equaled 0. And any way that you want to do it, we should get pi AB as the answer. Okay, so I would challenge you to kind of try to set it up the same way. Okay, we've done a lot of the work with the parameterizing up here for you already. Okay, so you could try the integrals with all the different setups if you would like to. Okay, then we have one more thing. This one gets a little bit weird to follow, but it comes in handy when you get into some really like abstract regions here. But anyways, we're going to draw some pictures here. Okay, so this would be D this would be c, and Green's theorem tells us that the double integral over d of dq dx minus dp dy dA equals closed interval over the region, or over the perimeter, dx plus q dy. Okay, now sometimes you might have more than one region, okay, and so you might have something, and this is getting us, this is kind of an intermediate step. You might be like, why would we do this? Well, let's say that we have something like this, okay, where maybe we split it into two regions, D1 and D2. Okay, and furthermore, we still have the positive orientation here, okay, but D1, like if you look, okay, if D1 has that counterclockwise orientation, then when we get to this border, we'd be going up, and for D2, we'd be going down. Okay, and we're going to call, what we really have made here is three different curves. So we have, I'll use my highlighter here. We have this guy, which would be C1. Oops. My pen is getting all glitchy now. How many times can I complain in my videos about my Chromebook? Somebody should count it up. Okay. And then we have what we're going to call over here. So it's kind of like the triangle one that we did earlier on, where we're going to split these borders into pieces because they're not a smooth curve. Okay. And then we'll have C3, but now we have to pick an orientation for C3 in order to draw it in, right? So what we might do here is say that this guy is C3 on D1, which means it's negative C3 on D2 to maintain the orientation. If C3 points up, then negative C3 has to point down, okay? So now our double integral over d of dq dx minus dp dy dA would be the integral of d1 plus your integral of d2. Okay, and so now we can split those up into their line integrals. So we would have the integral over C1 and C3. You know what, I'm just going to start calling that middle part star, so I don't have to keep rewriting it. Okay, plus the integral over C2 and negative C3. Okay, which the C3's cancel each other out basically. Okay, so it's a line integral over C1 plus your line integral over C2. So it's just your line integral over C1 and C2, just like that. Okay. I'm sorry, I kept writing dx, dy. That's not going to be star. Okay. Star would be p dx plus q dy. Okay? All right, so why? Because we will run into regions that aren't simply connected. So if I have a region that looks like this, okay, where this is D, and I've got a C2 and a C1, okay? This is not simply connected. It's got a hole in the middle, okay? So I cannot use Green's theorem here, okay? It has to be simply connected, piecewise smooth, all that junk, remember? But what I can do is split it up. So that's why we wanted to learn how to split up the region, because we learned first on one that didn't really need to be split up, but this one does. Okay, so now I'm going to split it up, and on top here, I'm going to have C1A, and on the bottom, I'm going to have C1B. Okay, so I've split curve C1 into the top half and the bottom half. And then same with C2, I'm going to have C2B and C2A, all right? And then I also have, I added in two new pieces there. I've got C3, which I'm going to maintain the orientation in C1, all the A's, I'm sorry. And then I'm going to have C4, okay, which means if I'm looking at the bottom region, D2, those C1 and C3s would have to be negative to maintain that counterclockwise orientation. Okay. So for this one then, if I wanted to do the double integral over d of dq dx minus dp dy dA, right, I could do it over d1 plus d2. Okay, which means I can split up some line integrals here, right? I can do it, so if I'm over d1, I've got C1A, C3, oops, I should use union signs here, C2A, C4, that's going to be P dx plus Q dy. And this is all the subscript here. So I'm just trying to save space. Plus, now I'm going to get D2. So I'm going to have C1b negative C4, C2b. That should be a union sign again. I keep writing plus. Negative C3. Okay, and then the C3s and the C4s cancel out. Okay, and then we have the integral C1 P dx Q dy plus the integral over C2 of P dx plus Q dy. Okay, so we can just do those two integrals, all right? That's kind of a proof. Like, you don't have to do all the middle stuff. When you see a hole, we know that we can do this. And you might think that those are two things that you would subtract, okay? But just remember, I kind of mentioned it has something to do with how everything in the interior just cancels out and you only have the edges. And the edges are both positively oriented. They're both, are actually C2 Yeah, C2 is, okay, they're both positively oriented, okay, which means that when you do the line integrals, they add up. It's clear to see C1 is positively oriented. It's harder to see that C2 is. So remember the whole idea here is that when it is simply connected, you are going counterclockwise, which seems like C2 is not. But remember the other way that I described it is if you walked along the curve, the region is to your left, and that's how it is for C2. If I were to walk around that curve C2, the region D is to my left, okay? So again, it has to do with everything on the interior canceling out, and we only worry about the edges. And if the edges are both positively oriented, we're summing there. Okay, if C2 was pointed in the opposite direction, that's when we would subtract. All right. I think I have one more thing. Oh yeah, I have an example here. I think I'm going to stop there because it is getting a little glitchy with my video. So I'm going to stop and I'm going to do another kind of more complex example in another video. Okay.